The Sun is the star at the center of the solar system. Venus is the second planet from the Sunday. Mercury is the Sun is the star at the center of the solar system. It is a massive, hot ball of plasma, inflated and heated by nuclear fusion reactions at its core. Part of this internal energy is emitted from its surface as light, ultraviolet, and infrared radiation, providing most of the energy for life on Earth. The Sun's radius is about 695,000 kilometers, 432,000 miles, or 109 times that of Earth. Its mass is about 330,000 times that of Earth, making up about 99.86% of the total mass of the solar system. Roughly 3/4 of the Sun's mass consists of hydrogen, 73%, the rest is mostly helium, 25%, with much smaller quantities of heavier elements, including oxygen, carbon, neon, and iron. The Sun is a G-type main sequence star, G2V, informally called a yellow dwarf, though its light is actually white. It formed approximately 4.6 billion years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered in the center, whereas the rest flattened into an orbiting disk that became the solar system. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. It is thought that almost all stars form by this process. Every second, the Sun's core fuses about 600 million tons of hydrogen into helium, and in the process converts 4 million tons of matter into energy. This energy, which can take between 10,000 and 170,000 years to escape the core, is the source of the Sun's light and heat. Far in the future, when hydrogen fusion in the Sun's core diminishes to the point where the Sun is no longer in hydrostatic equilibrium, its core will undergo a marked increase in density and temperature which will push its outer layers to expand, eventually transforming the Sun into a red giant. This process will make the Sun large enough to render Earth uninhabitable approximately 5 billion years from the present. After this, the Sun will shed its outer layers and become a dense type of cooling star, a white dwarf, and no longer produce energy by fusion, but still glow and give off heat from its previous fusion. The enormous effect of the Sun on Earth has been recognized since prehistoric times and was thought of by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun are the basis of some solar calendars. The predominant calendar in use today is the Gregorian calendar, which is based upon the standard 16th century interpretation of the Sun's observed movement as actual movement. The Sun is a G-type main sequence star that makes up about 99.86% of the mass of the solar system. The Sun has an absolute magnitude of plus 4.83, estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs. The Sun is a population I, or heavy element-rich, star. Its formation may have been triggered by shockwaves from one or more nearby supernovae. This is suggested by a high abundance of heavy elements in the solar system, such as gold and uranium, relative to the abundances of these elements in so-called population II, heavy element-poor, stars. The heavy elements could most plausibly have been produced by endothermic nuclear reactions during a supernova, or by transmutation through neutron absorption within a massive second-generation star. The Sun is by far the brightest object in the Earth's sky, with an apparent magnitude of A26.74. This is about 13 billion times brighter than the next brightest star, Sirius, which has an apparent magnitude of A1.46. 1 astronomical unit, about 150 million kilometers, 93 million miles, is defined as the mean distance of the Sun's center to Earth's center, though the distance varies, by about +/2.5 million km or 1.55 million miles, as Earth moves from perihelion on about January 3 to aphelion on about July 4. The distances can vary between 147,098,074 km, perihelion, and 152,097,701 km, aphelion, and extreme values can range from 147,083,346 km to 152,112,126 km. At its average distance, light travels from the Sun's horizon to Earth's horizon in about 8 minutes and 20 seconds, while light from the closest points of the Sun and Earth takes about 2 seconds less. The energy of this sunlight supports almost all life on Earth by photosynthesis, and drives Earth's climate and weather. The Sun does not have a definite boundary, but its density decreases exponentially with increasing height above the photosphere. For the purpose of measurement, the Sun's radius is considered to be the distance from its center to the edge of the photosphere, the apparent visible surface of the sunday. By this measure, the Sun is a near-perfect sphere with an oblateness estimated at 9 millionths, which means that its polar diameter differs from its equatorial diameter by only 10 kilometers, 6.2 miles. The tidal effect of the planets is weak and does not significantly affect the shape of the sunday. The Sun rotates faster at its equator than at its poles. This differential rotation is caused by convective motion due to heat transport and the Coriolis force due to the Sun's rotation. In a frame of reference defined by the stars, the rotational period is approximately 25.6 days at the equator and 33.5 days at the poles. Viewed from Earth as it orbits the Sun, the apparent rotational period of the Sun at its equator is about 28 days. Viewed from a vantage point above its north pole, the Sun rotates counterclockwise around its axis of spin. The Sun is the star at the center of the solar system. It is a massive, hot ball of plasma. Venus is the second planet from the sunday. Mercury is the first planet from the Sun and the smallest planet in the solar system. It is a terrestrial planet with a heavily cratered surface due to the planet having no geological activity and an extremely tenuous atmosphere, called an exosphere. Despite being the smallest planet in the solar system with a mean diameter of 4,880 kilometers, 3,030 miles, 38% of that of Earth, Mercury is dense enough to have roughly the same surface gravity as Mars. Mercury has a dynamic magnetic field with a strength about 1% of that of Earth's and has no natural satellites. According to current theories, Mercury may have a solid silicate crust and mantle overlying a solid outer core, a deeper liquid core layer, and a solid inner core. Having almost no atmosphere to retain heat, Mercury has surface temperatures that change wildly during the day, ranging from 100 K, 173 degrees C, 280 degrees F, at night to 700 K, 427 degrees Celsius, 800 degrees Fahrenheit, during sunlight across the equator regions. At Mercury's poles, though, there are large reservoirs of water ices that are never exposed to direct sunlight, which has an estimated mass of about 0.025% the Antarctic ice sheet. There are many competing hypotheses about Mercury's origins and development, some of which incorporate collision with planetesimal and rock vaporization. Because Mercury is very close to the Sun, the intensity of sunlight on its surface is between 4.59 and 10.61 times the solar constant, amount of the Sun's energy received at 1 astronomical unit, which is roughly the distance between Earth and the Sun. Mercury orbits the Sun in a 3:2 spin orbit resonance, meaning that relative to the background stars, it rotates on its axis exactly 3 times for every 2 revolutions it makes around the sunday. Counterintuitively, due to Mercury's slow rotation, an observer on the planet would see only 1 Mercurian solar day, 176 Earth days, every 2 Mercurian solar years, 88 Earth days each. Mercury's axis has the smallest tilt of any of the solar system's planets, about 1/30 of a degree, and its orbital eccentricity is the largest of all known planets in the solar system. Like Venus, Mercury orbits the Sun within Earth's orbit, making it appear in Earth's sky only as a morning star or evening star that's relatively close to the sunday. In English, it is named after the Roman god Mercurius, Mercury, god of commerce, communication, and the messenger of gods. Mercury is the most difficult planet to reach from Earth because it requires the greatest change in spacecraft's velocity. Only 2 spacecraft have visited Mercury as of 2023, Mariner 10 flew by in 1974 and 1975, and Messenger launched in 2004 and orbited Mercury over 4,000 times in 4 years. The Bepi-Colombo spacecraft is scheduled to make its final arrival at Mercury in 2025, and will then insert 2 orbiters. Mercury is one of 4 terrestrial planets in the Solar System, and is a rocky body like Earth. It is the smallest planet in the Solar System, with an equatorial radius of 2,439.7 kilometers, 1,516.0 miles. Mercury is also smaller, albeit more massive, than the largest natural satellites in the Solar System, Ganymede and Titan. Mercury consists of approximately 70% metallic and 30% silicate material. Mercury appears to have a solid silicate crust and mantle overlying a solid, iron sulfide outer core layer, a deeper liquid core layer, and a solid inner core. The planet's density is the second highest in the Solar System at 5.427 g/cm3, only slightly less than Earth's density of 5.515 g/cm3. If the effect of gravitational compression were to be factored out from both planets, the materials of which Mercury is made would be denser than those of Earth, with an uncompressed density of 5.3 g/cm3 versus Earth's 4.4 g/cm331. Mercury's density can be used to infer details of its inner structure. Although Earth's high density results appreciably from gravitational compression, particularly at the core, Mercury is much smaller and its inner regions are not as compressed. Therefore, for it to have such a high density, its core must be large and rich in iron. The radius of Mercury's core is estimated to be 2020 plus or minus 30 kilometers, 1255 plus or minus 19 miles, based on interior models constrained to be consistent with the value of the moment of inertia factor given in the info box. Hence, Mercury's core occupies about 57% of its volume. For Earth this proportion is 17%. Research published in 2007 suggests that Mercury has a molten core 3435. The mantle crust layer is in total 420 kilometers, 260 miles, thick. Based on data from the Mariner 10 and Messenger missions, in addition to Earth-based observation, Mercury's crust is estimated to be 35 kilometers, 22 miles, thick. However, this model may be an overestimate and the crust could be 26 plus or minus 11 kilometers, 16.2 plus or minus 6.8 miles, thick based on an ARRI ISO's TACE model. One distinctive feature of Mercury's surface is the presence of numerous narrow ridges, extending up to several hundred kilometers in length. It is thought that these were formed as Mercury's core and mantle cooled and contracted at a time when the crust had already solidified. Mercury's core has a higher iron content than that of any other major planet in the Solar System, and several theories have been proposed to explain this. The most widely accepted theory is that Mercury originally had a metal-silicate ratio similar to common chondrite meteorites, thought to be typical of the Solar System's rocky matter, and a mass approximately 2.25 times its current mass. Early in the Solar System's history, Mercury may have been struck by a planetesimal of approximately 1/6 Mercury's mass and several thousand kilometers across. The impact would have stripped away much of the original crust and mantle, leaving the core behind as a relatively major component. A similar process, known as the giant impact hypothesis, has been proposed to explain the formation of Earth's moon. Alternatively, Mercury may have formed from the solar nebula before the Sun's energy output had stabilized. It would initially have had twice its present mass, but as the proto-Sun contracted, temperatures near Mercury could have been between 2,500 and 3,500 K and possibly even as high as 10,000 K. Much of Mercury's surface rock could have been vaporized at such temperatures, forming an atmosphere of rock vapor that could have been carried away by the solar wind. A third hypothesis proposes that the solar nebula caused drag on the particles from which Mercury was accreting, which meant that lighter particles were lost from the accreting material and not gathered by Mercury. Each hypothesis predicts a different surface composition, and 2 space missions have been tasked with making observations of this composition. The first Messenger, which ended in 2015, found higher than expected potassium and sulfur levels on the surface, suggesting that the giant impact hypothesis and vaporization of the crust and mantle did not occur because said potassium and sulfur would have been driven off by the extreme heat of these events. Bepi Colombo, which will arrive at Mercury in 2025, will make observations to test these hypotheses. 47 The findings so far would seem to favor the third hypothesis, however, further analysis of the data is needed. Mercury is the first planet from the Sun and the smallest planet in the Solar System. It is a terrestrial planet with a heavily cratered surface due to the planet having no geological. Venus is the second planet from the Sunday. It is a rocky planet with the densest atmosphere. Venus is the second planet from the Sunday. It is a rocky planet with the densest atmosphere of all the rocky bodies in the Solar System, and the only one with a mass and size that is close to that of its orbital neighbor Earth. Orbiting inferiorly, inside of Earth's orbit, it appears in Earth's sky always close to the Sun, as either a morning star or an evening star. While this is also true for Mercury, Venus appears much more prominently, since it is the third brightest object in Earth's sky after the Moon and the Sun, appearing brighter than any other star like classical planet or any fixed star. With such prominence in Earth's sky, Venus has historically been a common and important object for humans, in both their cultures and astronomy. Venus has a weak induced magnetosphere and an especially thick carbon dioxide atmosphere, which creates, together with its global sulfuric acid cloud cover, an extreme greenhouse effect. This results at the surface in a mean temperature of 737 K, 464 degrees Celsius, 867 degrees Fahrenheit, and a crushing pressure of 92 times that of Earth's at sea level, turning the air into a supercritical fluid, while at cloudy altitudes of 50 kilometers, 30 miles, above the surface, the pressure, temperature, and also radiation are very much like at Earth's surface. Conditions possibly favorable for life on Venus have been identified at its cloud layers, with recent research having found indicative, but not convincing, evidence of life on the planet. Venus may have had liquid surface water early in its history, possibly enough to form oceans, but runaway greenhouse effects eventually evaporated any water, which then was taken into space by the solar wind. Internally, Venus is thought to consist of a core, mantle, and crust, the latter releasing internal heat through its active volcanism, shaping the surface with large resurfacing instead of plate tectonics. Venus is one of two planets in the Solar System which have no moons. Venus has a rotation which has been slowed and turned against its orbital direction, retrograde, by the strong currents and drag of its atmosphere. This rotation produces, together with the time of 224.7 Earth days it takes Venus to complete an orbit around the Sun, a Venusian solar year, a Venusian solar day length of 117 Earth days, the longest in the Solar System, resulting in a Venusian year being just under 2 Venusian days long. The orbits of Venus and Earth are the closest between any two Solar System planets, approaching each other in synodic periods of 1.6 years. While this allows them to come closer to each other at inferior conjunction than any other pair of Solar System planets, Mercury stays on average closer to them than any other planet, as Mercury is the most central planet and passes by most frequently. That said, Venus and Earth have between them the lowest difference in gravitational potential than any other pair of Solar System planets. This has allowed Venus to be the most accessible destination and attractive gravity assist waypoint for interplanetary flights. In 1961, Venus became the target of the first interplanetary flight in human history, followed by many essential interplanetary firsts like the first soft landing on another planet in 1970. These probes made it evident that extreme greenhouse effects have created oppressive surface conditions, an insight that has crucially informed predictions about global warming on Earth. This finding stopped most attention towards theories and the then popular science fiction about Venus being a habitable or inhabited planet. Crewed flights to Venus have been suggested nevertheless, either to fly by Venus, performing a gravity assist for reaching Mars faster and safer, or to enter the Venusian atmosphere and stay aloft at altitudes with conditions more comparable to Earth's surface, except atmospheric composition, than anywhere else in the Solar System. Contemporarily, Venus has again gained interest as a case for research into particularly the development of Earth-like planets and their habitability. Venus is one of the 4 terrestrial planets in the Solar System, meaning that it is a rocky body like Earth. It is similar to Earth in size and mass and is often described as Earth's sister or twin. Venus is close to spherical due to its slow rotation. Venus has a diameter of 12,103.6 kilometers, 7,520.8 miles, only 638.4 kilometers, 396.7 miles, less than Earth's, and its mass is 81.5% of Earth's. Conditions on the Venusian surface differ radically from those on Earth because its dense atmosphere is 96.5% carbon dioxide, with most of the remaining 3.5% being nitrogen. The surface pressure is 9.3 megapascals, 93 billion Argentine pesos, and the average surface temperature is 737 K, 464 degrees Celsius, 867 degrees Fahrenheit, above the critical points of both major constituents and making the surface atmosphere a supercritical fluid out of mainly supercritical carbon dioxide and some supercritical nitrogen. The atmosphere of Venus appears darker and lined with shadows. The shadows trace the prevailing wind direction. Cloud structure of the Venusian atmosphere, made visible through ultraviolet imaging. Venus has a dense atmosphere composed of 96.5% carbon dioxide, 3.5% nitrogen. Both exist as supercritical fluids at the planet's surface with a 6.5% density of water and traces of other gases including sulfur dioxide. The mass of its atmosphere is 92 times that of Earth's, whereas the pressure at its surface is about 93 times that at Earth's, a pressure equivalent to that at a depth of nearly 1 kilometer, 58 mi, under Earth's oceans. The density at the surface is 65 kg/m3, 4.1 lb/cu foot, 6.5% that of water, or 50 times as dense as Earth's atmosphere at 293 K, 20 degrees Celsius, 68 degrees Fahrenheit, at sea level. The CO2-rich atmosphere generates the strongest greenhouse effect in the solar system, creating surface temperatures of at least 735 K, 462 degrees Celsius, 864 degrees Fahrenheit. This makes the Venusian surface hotter than Mercury's, which has a minimum surface temperature of 53 K, 220 degrees C, 364 degree F, and maximum surface temperature of 700 K, 427 degrees Celsius, 801 degrees Fahrenheit, even though Venus is nearly twice Mercury's distance from the Sun and thus receives only 25% of Mercury's solar irradiance. Because of its runaway greenhouse effect, Venus has been identified by scientists such as Carl Sagan as a warning and research object linked to climate change on Earth. Venus temperature maximum 900 degrees Fahrenheit, 482 degrees Celsius, normal 847 degrees Fahrenheit, 453 degrees Celsius, minimum 820 degrees Fahrenheit, 438 degrees Celsius. Venus's atmosphere is rich in primordial noble gases compared to that of Earth. This enrichment indicates an early divergence from Earth in evolution. An unusually large comet impact or accretion of a more massive primary atmosphere from solar nebula have been proposed to explain the enrichment. However, the atmosphere is depleted of radiogenic argon, a proxy for mantle degassing, suggesting an early shutdown of major magmatism. Studies have suggested that billions of years ago, Venus's atmosphere could have been much more like the one surrounding the early Earth, and that there may have been substantial quantities of liquid water on the surface. After a period of 600 million to several billion years, solar forcing from rising luminosity of the Sun and possibly large volcanic resurfacing caused the evaporation of the original water in the current atmosphere. A runaway greenhouse effect was created once a critical level of greenhouse gases, including water, was added to its atmosphere. Although the surface conditions on Venus are no longer hospitable to any Earth-like life that may have formed before this event, there is speculation on the possibility that life exists in the upper cloud layers of Venus, 50 kilometers, 30 miles, up from the surface, where the atmospheric conditions are the most Earth-like in the solar system, with temperatures ranging between 303 and 353 K, 30 and 80 degrees Celsius, 86 and 176 degrees Fahrenheit, and the pressure and radiation being about the same as at Earth's surface, but with acidic clouds and the carbon dioxide air. The putative detection of an absorption line of phosphine in Venus's atmosphere, with no known pathway for abiotic production, led to speculation in September 2020 that there could be extant life currently present in the atmosphere. Later research attributed the spectroscopic signal that was interpreted as phosphine to sulfur dioxide, or found that in fact there was no absorption line. Types of cloud layers, as well as temperature and pressure change by altitude in the atmosphere, thermal inertia and the transfer of heat by winds in the lower atmosphere mean that the temperature of Venus's surface does not vary significantly between the planet's two hemispheres, those facing and not facing the Sun, despite Venus's slow rotation. Winds at the surface are slow, moving at a few kilometers per hour, but because of the high density of the atmosphere at the surface, they exert a significant amount of force against obstructions, and transport dust and small stones across the surface. This alone would make it difficult for a human to walk through, even without the heat, pressure, and lack of oxygen. Above the dense CO2 layer are thick clouds, consisting mainly of sulfuric acid, which is formed by sulfur dioxide and water through a chemical reaction resulting in sulfuric acid hydrate. Additionally, the clouds consist of approximately 1% ferric chloride. Other possible constituents of the cloud particles are ferric sulfate, aluminium chloride, and phosphoric anhydride. Clouds at different levels have different compositions and particle size distributions. These clouds reflect, similar to thick cloud cover on Earth, about 70% of the sunlight that falls on them back into space, and since they cover the whole planet they prevent visual observation of Venus's surface. The permanent cloud cover means that although Venus is closer than Earth to the Sun, it receives less sunlight on the ground, with only 10% of the received sunlight reaching the surface, resulting in average daytime levels of illumination at the surface of 14,000 lux, comparable to that on Earth in the daytime with overcast clouds. Strong 300 km per hour, 185 miles per hour, winds at the cloud tops go around Venus about every 4 to 5 Earth days. Winds on Venus move at up to 60 times the speed of its rotation, whereas Earth's fastest winds are only 10–20% rotation speed. The surface of Venus is effectively isothermal. It retains a constant temperature not only between the two hemispheres but between the equator and the poles. Venus's minute axial tilt less than 3 degrees, compared to 23 degrees on Earth, also minimizes seasonal temperature variation. Altitude is one of the few factors that affect Venusian temperatures. The highest point on Venus, Maxwell Montes, is therefore the coolest point on Venus, with a temperature of about 655 K, 380 degrees Celsius, 715 degrees Fahrenheit, and an atmospheric pressure of about 4.5 MPa, 45 bar. In 1995, the Magellan spacecraft imaged a highly reflective substance at the tops of the highest mountain peaks, a Venus snow that bore a strong resemblance to terrestrial snow. This substance likely formed from a similar process to snow, albeit at a far higher temperature. Too volatile to condense on the surface, it rose in gaseous form to higher elevations, where it is cooler and could precipitate. The identity of this substance is not known with certainty, but speculation has ranged from elemental tellurium to lead sulfide, galena. Although Venus has no seasons, in 2019, astronomers identified a cyclical variation in sunlight absorption by the atmosphere, possibly caused by opaque, absorbing particles suspended in the upper clouds. The variation causes observed changes in the speed of Venus's zonal winds and appears to rise and fall in time with the Sun's 11-year sunspot cycle. The existence of lightning in the atmosphere of Venus has been controversial 74 since the first suspected bursts were detected by the Soviet Venera probes. In 2006-07, Venus Express clearly detected Whistler mode waves, the signatures of lightning. Their intermittent appearance indicates a pattern associated with weather activity. According to these measurements, the lightning rate is at least half that on Earth, however other instruments have not detected lightning at all. The origin of any lightning remains unclear, but could originate from clouds or Venusian volcanoes. In 2007, Venus Express discovered that a huge double atmospheric polar vortex exists at the South Pole. Venus Express discovered, in 2011, that an ozone layer exists high in the atmosphere of Venus. On January 29, 2013, ESA scientists reported that the ionosphere of Venus streams outwards in a manner similar to the ion tail seen streaming from a comet under similar conditions. In December 2015, and to a lesser extent in April and May 2016, researchers working on Japan's Akatsuki mission observed bow-shaped objects in the atmosphere of Venus. This was considered direct evidence of the existence of perhaps the largest stationary gravity waves in the solar system. Venus is the second planet from the Sun. It is a rocky planet with the densest atmosphere of all the rocky. Earth is the third planet from the Sun and the only astronomical object known to harbor life. This is enabled by Earth being a water world, the only one in the solar system sustaining liquid surface water. Almost all of Earth's water is contained in its global ocean, covering 70.8% of Earth's surface. The remaining 29.2% of Earth's surface is land, most of which is located in the form of continental land masses within one hemisphere, Earth's land hemisphere. Most of Earth's land is somewhat humid and covered by vegetation, while large sheets of ice at Earth's polar deserts retain more water than Earth's groundwater, lakes, rivers, and atmospheric water combined. Earth's land is part of Earth's crust, consisting of several slowly moving tectonic plates, which interact to produce mountain ranges, volcanoes, and earthquakes. Earth has a liquid outer core that generates a magnetosphere capable of deflecting most of the destructive solar winds and cosmic radiation. Earth has a dynamic atmosphere, which sustains Earth's surface conditions and protects it from most meteoroids and UV light at entry. It has a composition of primarily nitrogen and oxygen. Water vapor is widely present in the atmosphere, forming clouds that cover most of the planet. The water vapor acts as a greenhouse gas and, together with other greenhouse gases in the atmosphere, particularly carbon dioxide, CO2, creates the conditions for both liquid surface water and water vapor to persist via the capturing of energy from the sun's light. This process maintains the current average surface temperature of 14.76 degrees Celsius, at which water is liquid under atmospheric pressure. Differences in the amount of captured energy between geographic regions, as with the equatorial region receiving more sunlight than the polar regions, drive atmospheric and ocean currents, producing a global climate system with different climate regions, and a range of weather phenomena such as precipitation, allowing components such as nitrogen to cycle. Earth is rounded into an ellipsoid with a circumference of about 40,000 kilometers. It is the densest planet in the solar system. Of the four rocky planets, it is the largest and most massive. Earth is about 8 light minutes away from the Sun and orbits it, taking a year, about 365.25 days, to complete one revolution. Earth rotates around its own axis in slightly less than a day, in about 23 hours and 56 minutes. Earth's axis of rotation is tilted with respect to the perpendicular to its orbital plane around the Sun, producing seasons. Earth is orbited by one permanent natural satellite, the Moon, which orbits Earth at 384,400 kilometers, 1.28 light seconds, and is roughly a quarter as wide as Earth. Through tidal locking, the Moon always faces Earth with the same side, which causes tides, stabilizes Earth's axis, and gradually slows its rotation. Earth, like most other bodies in the solar system, formed 4.5 billion years ago from gas in the early solar system. During the first billion years of Earth's history, the ocean formed and then life developed within it. Life spread globally and has been altering Earth's atmosphere and surface, leading to the Great Oxidation Event 2 billion years ago. Humans emerged 300,000 years ago in Africa and have spread across every continent on Earth with the exception of Antarctica. Humans depend on Earth's biosphere and natural resources for their survival, but have increasingly impacted the planet's environment. Humanity's current impact on Earth's climate and biosphere is unsustainable, threatening the livelihood of humans and many other forms of life, and causing widespread extinctions. The oldest material found in the solar system is dated to 4.5682 plus 0.0002 0.0004 Ga billion years ago. By 4.54 plus or minus 0.04 Ga, the primordial Earth had formed. The bodies in the solar system formed and evolved with the Sunday. In theory, a solar nebula partitions a volume out of a molecular cloud by gravitational collapse, which begins to spin and flatten into a circumstellar disk, and then the planets grow out of that disk with the Sunday. A nebula contains gas, ice grains, and dust, including primordial nuclides. According to nebular theory, planetesimals formed by accretion, with the primordial Earth being estimated as likely taking anywhere from 70 to 100 million years to form. Estimates of the age of the Moon range from 4.5 Ga to significantly younger. A leading hypothesis is that it was formed by accretion from material loosed from Earth after a Mars-sized object with about 10% of Earth's mass, named Gaia, collided with Earth. It hit Earth with a glancing blow and some of its mass merged with Earth. Between approximately 4.1 and 3.8 Ga, numerous asteroid impacts during the late heavy bombardment caused significant changes to the greater surface environment of the Moon and, by inference, to that of Earth. Earth's atmosphere and oceans were formed by volcanic activity and outgassing. Water vapor from these sources condensed into the oceans, augmented by water and ice from asteroids, protoplanets, and comets. Sufficient water to fill the oceans may have been on Earth since it formed. In this model, atmospheric greenhouse gases kept the oceans from freezing when the newly forming Sun had only 70% of its current luminosity. By 3.5 Ga, Earth's magnetic field was established, which helped prevent the atmosphere from being stripped away by the solar wind. As the molten outer layer of Earth cooled, it formed the first solid crust, which is thought to have been mafic in composition. The first continental crust, which was more felsic in composition, formed by the partial melting of this mafic crust. The presence of grains of the mineral zircon of Hadean age in Eoarchean sedimentary rocks suggests that at least some felsic crust existed as early as 4.4 Ga, only 140 Ma after Earth's formation. There are two main models of how this initial small volume of continental crust evolved to reach its current abundance, a relatively steady growth up to the present day, which is supported by the radiometric dating of continental crust globally, and an initial rapid growth in the volume of continental crust during the Archean, forming the bulk of the continental crust that now exists, which is supported by isotopic evidence from hafnium in zircons and neodymium in sedimentary rocks. The two models and the data that support them can be reconciled by large-scale recycling of the continental crust, particularly during the early stages of Earth's history. New continental crust forms as a result of plate tectonics, a process ultimately driven by the continuous loss of heat from Earth's interior. Over the period of hundreds of millions of years, tectonic forces have caused areas of continental crust to group together to form supercontinents that have subsequently broken apart. At approximately 750 Ma, one of the earliest known supercontinents, Rodinia, began to break apart. The continents later recombined to form Pan-Oceania at 605-40 Ma, then finally Pangaea, which also began to break apart at 180 Ma. The most recent pattern of ice ages began about 40 Ma, and then intensified during the Pleistocene about 3 Ma. High and middle latitude regions have since undergone repeated cycles of glaciation and thaw, repeating about every 21,000, 41,000, and 100,000 years. The last glacial period, colloquially called the last ice age, covered large parts of the continents, to the middle latitudes, in ice, and ended about 11,700 years ago. Artists' impression of the Archean, the eon after Earth's formation, featuring round stromatolites, which are early oxygen-producing forms of life from billions of years ago. After the late heavy bombardment, Earth's crust had cooled, its water-rich barren surface is marked by continents and volcanoes, with the Moon still orbiting Earth half as close than today, appearing 2.8 times larger and producing strong tides. Chemical reactions led to the first self-replicating molecules about 4 billion years ago. A half billion years later, the last common ancestor of all current life arose. The evolution of photosynthesis allowed the sun's energy to be harvested directly by life forms. The resultant molecular oxygen accumulated in the atmosphere, and due to interaction with ultraviolet solar radiation, formed a protective ozone layer in the upper atmosphere. The incorporation of smaller cells within larger ones resulted in the development of complex cells called eukaryotes. True multicellular organisms formed as cells within colonies became increasingly specialized. Aided by the absorption of harmful ultraviolet radiation by the ozone layer, life colonized Earth's surface. Among the earliest fossil evidence for life is microbial mat fossils found in 3.48 billion-year-old sandstone in Western Australia, biogenic graphite found in 3.7 billion-year-old metasedimentary rocks in western Greenland, and remains of biotic material found in 4.1 billion-year-old rocks in Western Australia. The earliest direct evidence of life on Earth is contained in 3.45 billion-year-old Australian rocks showing fossils of microorganisms. During the Neoproterozoic, 1000 to 539 Ma, much of Earth might have been covered in ice. This hypothesis has been termed snowball Earth, and it is of particular interest because it preceded the Cambrian explosion, when multicellular life forms significantly increased in complexity. Following the Cambrian explosion, 535 Ma, there have been at least 5 major mass extinctions and many minor ones. Apart from the proposed current Holocene extinction event, the most recent was 66 Ma, when an asteroid impact triggered the extinction of the non-avian dinosaurs and other large reptiles, but largely spared small animals such as insects, mammals, lizards, and birds. Mammalian life has diversified over the past 66 mice, and several million years ago an African ape species gained the ability to stand upright. This facilitated tool use and encouraged communication that provided the nutrition and stimulation needed for a larger brain, which led to the evolution of humans. The development of agriculture, and then civilization, led to humans having an influence on Earth and the nature and quantity of other life forms that continues to this day. A dark gray and red sphere representing the Earth lies against a black background to the right of an orange circular object representing the Sun. Conjectured illustration of the scorched Earth after the Sun has entered the red giant phase. About 5-7 billion years from now Earth's expected long-term future is tied to that of the Sunday. Over the next 1.1 billion years, solar luminosity will increase by 10%, and over the next 3.5 billion years by 40%. Earth's increasing surface temperature will accelerate the inorganic carbon cycle, reducing CO2 concentration to levels lethally low for plants, 10 ppm for C4 photosynthesis, in approximately 100-900 million years. The lack of vegetation will result in the loss of oxygen in the atmosphere, making animal life impossible. Due to the increased luminosity, Earth's mean temperature may reach 100 degrees Celsius, 212 degrees Fahrenheit, in 1.5 billion years, and all ocean water will evaporate and be lost to space, which may trigger a runaway greenhouse effect, within an estimated 1.6 to 3 billion years. Even if the Sun were stable, a fraction of the water in the modern oceans will descend to the mantle, due to reduced steam venting from mid-ocean ridges. The Sun will evolve to become a red giant in about 5 billion years. Models predict that the Sun will expand to roughly 150 million km, 93 million mi, about 250 times its present radius. Earth's fate is less clear. As a red giant, the Sun will lose roughly 30% of its mass, so, without tidal effects, Earth will move to an orbit 1.70, 250 million km, 160 million mi, from the Sun when the star reaches its maximum radius. Otherwise, with tidal effects, it may enter the Sun's atmosphere and be vaporized. Earth is the third planet from the Sun and the only astronomical object known to harbor life. This is enabled by Earth being a water world, the only one in the solar system